I'm at Stockholm University, and I'm also working for a company building a forecasting tool called Indicio Technologies. So I will talk about subsampling Markov chain Monte Carlo for Bayesian variable selection and model averaging in BGNLM. First, to give a short overview of what I will be talking about. First, I will give some background, sort of set the scene to the work that has been done, and then I will outline the contribution, and then finally give some examples to demonstrate how what we have done works. So first, we have Bayesian generalized nonlinear models. It can be thought of as an extended Bayesian GLM with nonlinear transformations through something that we call features. It is a way to model a possibly nonlinear relationship between a dependent variable y and a set of m covariates x. And I will, on the next slide, go into a bit more of some of the components here. But here we have the link function linking the mean to the linear predictor. And that works just like in a regular GLM. But then we have the gamma j parameters, which they indicate if a specific feature is included in the model or not. And this can be compared with Bayesian variable selection, where you have gamma j parameters determining if a covariate is the probability of including a covariate in the model or not. And in the setting of BGNLM, these use a complicated prior, which penalizes more complex features over more simple ones. The model parameters beta j use the Jeffreys prior. And then finally, we have the features, which is sort of what sets BGNLM apart from GLM or Bayesian GLM. They are possibly recursive nonlinear transformations of one or more of the covariates. So just put a simple example here. One feature could, for example, be have its own three parameters, alpha 0 through alpha 2, and it's the sign of alpha 0 plus alpha 1 x1 plus alpha 2 x4. So can take on very many shapes. Features as such are very flexible, but here we go through how we define the feature space. So what we first need is a set of nonlinear functions, and these can depend on the application, but they're just fed into the model. That this is the different nonlinear functions the model is allowed to use. And then we have three types of different modifications that can be applied to a feature. So we define this sort of in a recursive manner, where we begin with the bare covariates, and then we have these modifications that can be applied multiple times to the features. First, we have a nonlinear transformation, just like in the example with the sign. And then we have a modification, which implies taking an existing feature and applying one of the nonlinear functions to it. And finally, we have the multiplication modification, which just takes two features and multiplies them with each other. Since this is a recursive structure, it more or less, it creates a very large feature space. And if we don't limit it somehow, it's going to be infinite. To make sure that the feature space is finite, we have a limit on operations count per feature. So the number of modifications and covariates included, to make sure that the feature space is clearly defined and finite. To fit such a model to data, you need some kind of algorithm. And if we were to use regular MCMC to explore the feature space, we would require to be able to enumerate the full feature space. And if we have a very large feature space, this might either not be feasible or not even possible. So to solve this, the MCMC sampler is embedded within a genetic algorithm called genetically modified MJ-MCMC or GMJ-MCMC. And this algorithm works by first considering the population of just the covariates. And this population is explored. So we go to different models and evaluate them. And this population is explored using MCMC. And then the genetically modified part comes in, where we take this population of features that we have and features of high probability we apply modifications to, and features with low probability are removed from the population, thus generating a new population. And this process is repeated for a set number of populations, and it's also usually run with many threads in parallel to thoroughly explore the feature space. So if we consider for each model that the MCMC sampler visits, we require the marginal posterior of the model. One way to obtain that is, of course, through simulation, but that usually becomes quite expensive. And remember that we're looking at a very large number of possible different models. So much quicker alternative is to use a Laplace approximation. It's much faster usually, but it's still slow for large samples if we have a lot of data, as it requires the maximum likelihood estimate of the model parameters. But once we have all some way of obtaining the marginal posterior of the model, we can then calculate either the Monte Carlo model probability, which is just the relative frequency of how often we stop at this particular model. And we also have the more quickly converging renormalized estimator, which is just using Bayes' theorem to calculate the model's marginal posterior, or the model probability. And in these formulas here, we have T, which is the current iteration we're at. So we can calculate these for each step in the process. Moving on, we were, as mentioned in the beginning, interested in the posterior marginal probability for the different features. And given that we have calculated the model probabilities, we can immediately map from them to the feature probabilities. So we can do that more or less the same way, given either the Monte Carlo or the normalized estimates. And it just consists of summing over which models this feature was included in. Moving on to the contribution, we'll talk a bit about subsampling more in general, and then introduce the time inhomogeneous Markov chain Monte Carlo algorithm that we introduced in a previous paper. And then I will discuss the contribution of this short conference paper to merge TI MCMC within GMJ MCMC. So if we were to work without subsampling, the MLE theta hat is obtained through some optimization method. It can be Newton's method or gradient descent, as two general examples. Each iteration of this optimization function is going to go through all the data. And for a first order method such as gradient descent, the complexity scales linearly. And for a second order optimization method like Newton's method, we're going to see a quadratic complexity scaling. So a large number of observation is going to quickly make a second order optimization method slow, but also a first order. With subsampling, we can approximate or obtain an approximate maximum likelihood estimate, which we denote theta tilde, much quicker. And this is due to that we're only using a subsample of the data at each iteration. One common example of this is stochastic gradient descent, which is commonly used within machine learning, where you usually have a very large amount of data. And if we, after obtaining this approximate MLE estimate, we can do a final step calculating the likelihood of this model by using all the data. And that makes sure that this estimate is always going to be smaller than the estimate of the actual MLE, the exact MLE. And this is going to be important later when we look at how this TI MCMC works. Yes, so in a previous paper, we introduced this time inhomogeneous MCMC algorithm. And what it does, it allows the MLE estimates, theta tilde m, or for model M, they are allowed to change over time. So we add a T superscript denoting that this is the estimate we had at a specific time T. The last MLE estimate for each model is saved after we have visited it. And the next visit to the same model can then decide how to update the MLE estimate. It can either continue optimization from the last estimate or estimate a new MLE and compare the likelihood to see if we were closer to the exact MLE. And this has been shown to work with any optimization method which converges, but it has only been applied to linear models previously. So what we propose here is to use TI MCMC within the populations of GMJ MCMC in place of regular MCMC. We have also modified, we built an R package for GMJ MCMC during the previous research, and we have modified that to allow this. We're using something from the previous paper here. It's theorem 1 from the paper. So if we assume that the MLE estimates generate a sequence where a subsequent visit is going to provide a higher probability for a model or an equal probability for a model compared to a previous visit, and the sequence converges either almost surely or in probability. And we can see that we obtain this by the calculation of the likelihood from the full data set in the end of the optimization. If this is fulfilled, then the Markov chain will be both irreducible and recurrent. And for the renormalized estimator, it also holds that it will converge corresponding to if this sequence converges almost surely, we will see almost surely convergence here. And if we see convergence in probability, we will also have it here. Moving forward to the demonstration, we have run 3 examples, and we're using a optimization algorithm that we developed ourselves called Subsampling iteratively reweighted least squares with stochastic gradient descent. Quite a mouthful, but what we do is we run IRLS, which is sort of a Newton's method with subsampling, to create starting values for stochastic gradient descent. And you can use any optimizations method that converges according to the theorem, but we have shown empirically that this one works quite well. The first example is just a reproduction, no subsampling, and then we have a simulation study with toll data, which implies that the number of observations is orders of magnitude larger than the number of covariates. And finally, we have a predictive example with the abalone shell dataset. Looking at the first example, we have it's just a reproduction from the original paper on BGNLM. What we're doing is that we're using data from the Open Exoplanet catalog with 11 covariates and 223 observations to recover Kepler's third law, which I'm not fully up to date exactly what it says, but it's the formulation he came up with whilst studying planets a long time ago. And the model is able to, from the data, recover this exact formulation of the law. So we get quite interpretable results. And if we look here briefly at our table of results, we can see that we have the results that we obtained with the new implementation of GMJ and MCMC. And then we have the results from the original implementation. So we can see that we are quite similar in power and false detection rate. We're still a bit worse, meaning that there's probably some fine tuning that we could do, which we haven't been able to do yet. But this just shows that the new implementation of GMJ and MCMC works as intended. Moving on, we have our second example. It's a much larger sample size than the Kepler example. We have 50 binary covariates and 100,000 observations. The binary covariates are all IID, Bernoulli 0.5. And then we have our dependent variable y, which is normally distributed around a linear function with some multiplication of the covariates. We have here our beta vector of the data generative features, and it's set to 0 otherwise. And y was specified as this sort of complicated, more so as we get later into the equation, multiplications of the different features. And then we ran this using the time inhomogeneous MCMC and the SIRLS SGD algorithm within GMJ MCMC. And we calculated the power and the false detection rate. We can see here that we have the results with subsampling and then the results without subsampling, so using the full sample. And we can see that we are, as expected, we're not as good in getting the exact hits as we would be if using the full subsample, but we have saved a lot of computational complexity. I think some of the examples perhaps could take up to 24 hours to run, and using subsampling, it's much quicker to run. But you lose some accuracy, of course. The final example, we have the abalone shell dataset. It's available at the URL here. It's quite common dataset to use for evaluating different machine learning methods, testing for prediction. We have 4,177 observations, and we kept 1,000 of these for testing. Then we ran the algorithm with a 10% subsample size in SRLS SGD, and we ran 32 threads in parallel. And we also ran the same thing without subsampling. And we can see here that the subsampling is very similar in both RMSE, mean average error, and correlation to the non-subsampling. So more or less within the same level. We can also see that from a previous paper, we took results from a lot of different other algorithms which were on different models. And we can see that these are perhaps not tuned fully, but the main thing we want to point out here is that we get similar results as all these different methods like random forest, Bayesian GLM, lasso, variational Bayes. The main takeaway is that even using subsampling, we get very good results, and we are quicker to run the full estimation. Yes, thank you for listening. Any questions?
Very good, Jon. Thank you for the talk, and we are very much on time, so we actually have quite a bit of time for questions, and I don't see any questions in the chat. But then, if anyone has any questions to ask, it's just about to raise your hands probably and ask, because we have plenty of time for questions to Jon.
Or maybe everything was clear.
I might ask a very short question. So you mentioned that at the end of the optimization, you're still using the full sample to compute the likelihood to compare between the models. So yes. How crucial is this step, and how much you can expect that this can be improved further?
Yes, so if we're using a second order optimization algorithm, we're going to have n squared as complexity, or as the dominating complexity. And then just using the full data once in the end is going to be complex by a factor of n. So that way we're going to be much better. If we instead are using a first order optimization algorithm like gradient descent, we're going to see each iteration of the gradient descent is going to be n complex, whereas the final step is also going to be n complex. But if we then use subsampling, the final step is going to be the more complex one. But usually when you're using stochastic gradient descent, you require at least a few hundred, but often a few thousand iterations. So you're still going to see probably an improvement. We're also investigating a way to split, so we only use part of the data for that final step, but do so in a structured manner so that we can evaluate against different parts of the data and still fulfill the requirements of the theorem.